Hello everyone, my name is Chen Wei from Nanjing University. In this video, I'm going to present our work, Conflict-Aware Inference of Python Computable Runtime Environments with Domain Knowledge Graph. As one of the most popular high-level programming languages, code sharing and reuse of Python code have become a common practice for programmers. Empirical researchers observed that the Python code snippets on Stack Overflow is 76% parsable and 25% runnable, and only 24.4% of the Python code snippets shared through GitHub are executable in a clean Python 2 environment. The environment configuration issues are often caused by third-party package resources, triggering dependency errors. Programmers usually spend between 20 minutes and 2 hours to set up the environment, and in some cases, they even cannot restore a runtime environment. So, how to infer Python computable runtime environments? Let's see a motivation example. A naive approach installs the Python packages with the same names as the imported top-level models in the import statements. However, this approach fails to infer dependencies in many cases. URLlib2 is a standard model in Python 2 and has been split into several models in Python 3. Readcap does not exist on PyPI, and the package corresponding to it is PyCap. The last version of InfluxDB that contains the attribute InfluxDB cluster client is free. Furthermore, installing the latest versions of OpenFisca Core and JPKit causes a dependency conflict in transitive dependency NumPy. So we should select the appropriate versions for the packages to ensure compatibility. Surely the inferred packages need to contain the attributes used in the code. In general, there are 4 challenges. First, we should inference an appropriate Python version by the syntax or built-in resources. Second, it's common in practice that the name of a model imported in Python code does not match the name of the Python package it belongs to. Third, it's hard to know the mappings between used attributes and the specific versions. Last, dependency solving should ensure that all dependencies are compatible with the rest of inferred environment. In a word, the challenges are essentially the lack of domain knowledge. So we consider it as a task of knowledge graph for software engineering. This is an overview of our approach, PyCRE. The upper portion of the figure shows the construction of our Python package knowledge graph, which maintain a great deal of domain knowledge. The bottom portion shows the automatic inference of computable runtime environments. With the knowledge graph, PyCRE passes a target Python code, discovers its candidate libraries, and generates the computable runtime environment through dependency solving. We design an ontology for Python third-party packages to represent the relationships between the entities in real world. Package node stores its name as a property, which is normalized and unified. A version node contains its standard version identifier and the install status of the corresponding release. Model node stores fully qualified name and the import status that indicates whether the model can be successfully imported. Unlike model nodes, attributes with an identical name are defined as a single entity. Attributes can be a variable, function, class, or any content available in the corresponding model. For relationships, it's important to note that models may have submodels, and the requires age has a requirement property to save the version specifier. To extract domain knowledge, we first record the installation status by installing each version of packages. Then we get the dependency requirements of each successfully installed version from its metadata field. At last, we acquire the knowledge of models and their attributes. The whole process is automated, and we can check for new packages and versions to incrementally upgrade the KG, which is also automated. To utilize the only input, we fully pass the target code into an abstract syntax tree in clean Python environments, and then work in the AST for imported models and code attributes. It's worth mentioning that the name in from import statement can be a submodel, function, class, variable, or any attribute that can be accessed in the model. The results of target code parsing can be used to infer the candidate Python versions. We pass the code in Python 2 and 3 respectively. Then the Python versions with the fewest imported models and no syntax errors are the candidates. We represent the imported models and the code attributes as a forest. Each path tree in the forest has a top-level model name as a root node, and contains all the submodels and attributes of that model in the code. For each path tree in the forest, we query the corresponding knowledge graph to discover candidate libraries. We calculate the matching degree for models and attributes in order, reducing the search space step by step. Widely used string similarity metrics are not applicable here because the fully qualified name represents the reference path. So we define a metric based on the longest prefix match of the reference path. We query our KGs for all transitive dependencies of the candidate libraries, forming a directed graph called a dependency graph. We expect a subgraph of the dependency graph, satisfying all version specifications, which means no dependency conflict in the inferred environment. Dependency solving is often considered as the SAT problem and has been proved NP-complete. And we propose an efficient heuristic graph transformer algorithm for dependency solving. The installation order of all packages is generated by topological sorting, which ensures that all dependencies of a package are installed ahead of time. We first briefly introduce the SAT solver. With the dependency graph, each node corresponding to a Boolean variable and its constraints are encoded as a Boolean formula in conjunctive normal form. Let's see one of those for example. A version node is incompatible with the versions of its direct dependencies that do not meet the specific requirements, which would be translated into this Boolean class. However, there are no priority in the answers provided by the solver. For time efficiency and compliance with version selection priorities, our algorithm has two heuristic strengths. One is priority. We prefer the latest compatible version that can be successfully installed, since the latest version is usually downward compatible with previous versions and contains new resources. Another is pruning. If one version of a package is incompatible, We skip the other versions with identical dependency requirements because they would cause the same conflicts. When the currently selected version of a package does not satisfy the newly added version constraints, the current version and all its dependencies need to be removed from the subgraph. We only backtrack on the current search path when we encounter a dependency conflict, which is highly efficient, but in rare cases may miss solutions. So we call a set solver as the fallback to ensure the completeness of our algorithm when it claims that there is no solution. In addition to our PyCRE, 4 comparative methods are assessed in the evaluations. The first is Gistable, which attempts to install the Python packages with the same names as the imported top-level models, and does not use any knowledge. Second is Docker.me, which infers the runtime environments based on a pre-built knowledge base, without considering Python versions nor specific dependency versions. Third is V2, which reuses the inference results of Docker.me as the starting environments in Python 2 and Python 3, and guides the version changes by the error messages by code execution until finding a working environment. The last is SnifferDog, which uses a pre-built API bank to restore the execution environments of notebooks. We conduct our experiments on the Gistable dataset, which is a real-world dataset built from GitHub and contains 10,250 single-file Python code snippets. We evaluate the knowledge graph and the inference separately. For the fairness of our experiments, all methods should acquire knowledge for the same Python packages. This process is indeed time-consuming, which takes about 135 hours using 20 normal PCs, but it can be easily accelerated by parallelization. There are over 10 million entities and over 100 million relationships in our knowledge graph. We evaluate the effectiveness and the efficiency of PyCRE in inferring Python compatible runtime environments compared with the related work. Since only our PyCRE and V2 can infer the Python version for target code, we conduct the experiments in 3 environments: Python 2, Python 3, and the inferred Python versions. The most intuitive assessment is the ability to resolve import error. As shown in the table, PyCRE resolves the most import error in all 3 different settings, and is significantly better than the comparative methods. Another valuable metric is the number of working environments, which indicates the ability of an inference method to restore the runtime environments of Python code. PyCRE also infers a successfully runnable environment for the most Python code snippets. Inference time is a crucial metric for the efficiency of inference methods and represents the user's waiting time, which is one of the most important performance metrics for software. We only consider the 5,655 GISTs that have at least one third-party package and have no timeouts in all methods. The inference time of Docker.me and PyCRE, which fully uses pre-built knowledge bases, are short and comparable. To validate the effectiveness of our proposed heuristic algorithm, we exclusively use the set solver to conduct an ablation experiment, which is called PyCIE set only. As we can see, the heuristic algorithm is superior to set only in both effectiveness and efficiency. Especially, the longest time of our heuristic algorithm is much lower than the set solver, and the difference would become more significant as the size of the dependency graph increases due to the different time complexity. Based on our analysis, our heuristic algorithm solves 99.4% code snippets for which have at least one dependency and a compatible solution. We believe the approximation of our heuristic algorithm is good. In future work, we will acquire knowledge for more Python packages. We also plan to add the deprecation information of models and APIs into the knowledge graph to further infer appropriate versions. Besides, we will consider the compatibility between the inferred environments with local dependencies, which is more general in practice. Finally, we will apply our approach to other languages with transitive dependencies, such as Node.js. In this paper, we propose an approach to automatically inferring Python-compatible runtime environments with domain knowledge graph. First, we design a domain-specific ontology for Python third-party packages and propose an automatic approach to constructing the Python package knowledge graph. Second, we define a new metric of matching degree to discover required libraries. Moreover, we consider the compatibility of the inferred Python environments and design an efficient heuristic algorithm for dependency solving. Finally, we evaluate our approach with real-world Python code snippets on Gitable and shows the superior effectiveness and efficiency of our approach. The source code of PyCIE is open on GitHub. Thanks for watching.